Okay, this particular set of notes is only going to cover polar circles. I'm going to break all of the notes up into separate shapes so that you can watch them in chunks depending on what you may or may not need to watch or may miss. So the first shape that you guys investigated in your exploration was just r equals a constant. Theta's not even in the equation. And so what that means is that no matter what your angle, r is always going to be equal to 4. So the points that you're plotting will face every angle, and you will walk towards that angle. And one thing that we will never do is we will never do our 45-degree angles in this unit. We're going to give you the decimal values for your 30s and your 60s so that you can calculate numbers when necessary. But we're only going to do our 0s, 30s, 60s, 90s, and so on. And one thing you may notice as I fill in this table is that r is always equal to 4, and my angles are, once again, all my 30s, 60s, 90s, and so forth. But I'm only going from 0 to 180. And that is one thing that's going to be true all of the time in this unit, because when I have an equation that, in this case, is going to be a circle, and once we've investigated this, you will confirm that, I don't have to do points for every single part of the circle. If I have half the circle, then I can reflect to get the other half. So if I plotted 4 towards 0 degrees, which is 1, 2, 3, 4 right there, and then 4 rings out towards 30 degrees, 4 rings out towards 60, 4 rings out towards 90, 4 towards 120, towards 150, and towards 180, then I've generated the top half of that circle. So I take all those points and I simply keep drawing them. I mirror image them across the x-axis. But the other thing is that I'm also, you notice that all these points lie on the same ring of the polar grid, which of course is just because my constant happens to be an integer. If it was 4.5, it would go smack dab in between the 4th and the 5th ring, essentially. But the shape that that table generated is a perfect circle. That circle is also a circle that is centered at the pole. And so when we convert this into a Cartesian equation, we do it just like we did on the polar coordinate notes. We start out by replacing r with plus or minus the square root of x squared plus y squared. And remember what I said in those polar coordinate notes, we're going to give you these kinds of formulas, your right triangle trig formulas and that kind of thing, Pythagorean theorem. You'll need to know what to do with them, but we don't leave our equation like this. We want it to look like the equation for a circle. So what I'm going to do is I'm going to square both sides. And that'll get rid of the plus or minus the square root. And so I'll have x squared plus y squared is equal to 16. And so there's my Cartesian equation of a circle. And it confirms that the location of my center is 0, 0, and that my radius is 4. And that's because back in geometry and in Algebra 2, you guys learned that x squared plus y squared equals r squared was the parent circle, centered at the origin with a radius of r. And so what we can guess about in a polar equation with r equals -3, the negative ends up not mattering because that means that we're still going 3 units out from the pole. We're just going away from the angle. But since we're going all the way around, we're still going to generate a circle, still going to be centered at the pole, and it's still going to have a radius that's equal to 3. Okay, and you can always do a table of values to confirm this until you get enough practice with these. So what I want you guys to do is I want you to pause it, and I want you to try to do this table just like we did in the polar coordinate notes. I'll go ahead and I'll do the first 2 or maybe 3 to get you started and make sure everybody's on the right track, because this one actually does have a theta in the equation. And so r is going to be -2 times sine of 0 degrees, and sine of 0 degrees is 0. So that means I end up getting 0. And so my R value ended up being 0 when my angle was 0 degrees. So I'm going to put a point 0 units out towards 0 degrees. That's right on the pole. And so then I do R is equal to -2 sine of 30 degrees. And sine of 30 degrees is 1/2. And so I end up getting an answer of -1 towards 30 degrees. And so it sounds strange to say towards 30 degrees, but remember that's the angle you're facing towards. You're going to walk 1 unit away from it. So that puts you in the first ring right there. And then you do R is -2 sine of 60 degrees. And you go from there. So I want you to pause it, and I want you to go ahead and try and finish the rest of the table for yourself.
Wait.
Okay, so you should have taken a minute and finished filling in the table. And what we're going to do is we're going to give you guys the decimal values for things like this. It's about 1.73. We're just going to estimate that it's 1.7. Anytime that we graph it, it's not going to end up mattering at all. So we've got the first 2 points plotted. So this third point's going to go at -1.7, 60 degrees. So turn and face 60 degrees, but go 1.7 units away from it. So that would put a point right about there. Then go -2 units away from 90 degrees, which would be 2 units down away from 90 degrees. And then -3, or negative square root of 3 towards 120 degrees. So we're going to go 120 degrees and then rotate or walk 1.7 units away from it. And then -1 away from 150 degrees puts us there again. And then 0, 180 puts us back on top of the pole. And so what we've done is we've generated an entire circle. I want you to notice that this equation has sine in it. And the sine trig function is normally equated to the y variable. And that's why this circle has symmetry over the y-axis. It's also why it got shifted vertically off of the pole instead of horizontally. And so what we're going to see is we're going to see that when we do the next step, which is to convert it to Cartesian form. So when I convert this one to Cartesian form, remember from the earlier notes, you can go in a couple of different orders, but usually the best way is to go ahead and change sine to its definition, which is y over r. And then remember, this is, I told you before, this is r over 1 essentially, so that r is going to multiply up across. So we would have r squared is equal to -2y. And since x squared plus y squared is equal to r squared, that means that technically we could be done because we have converted into Cartesian form. I'm going to go ahead and not just convert into Cartesian form, I'm going to convert into graphing form for the Cartesian for a couple of reasons. First of all, we have historically done things like give an extra credit for it from time to time. Also because it's very good review and practice for the next unit, which is conics. And also it confirms the symmetry and the other characteristics that we're going to be talking about here in just a minute when we do our summary page. So if I wanted to convert it into its graphing form, that means that what I would need to do is complete the square. This is still a circle, but it's a circle that's been shifted off of the pole. And so your transformed circle equations look like this. It's done some kind of shifting. Now our circle has only done vertical shifting. So when I start rearranging my equation, I'm going to add the 2y to move it over, and I'm going to leave a blank right here. Because unfortunately, you are going to have to remember how to complete the square in order to earn that potential, sometimes extra credit, for converting into graphing form. So I want to remind you guys really quickly how you do that. Remember that when you want to complete the square, our x's are already a perfect square right there. I need my y's to become a perfect square. So that means I need to figure out what number would go right here. That would make my y group a perfect square, and that's 2 steps. Take this middle term and chop it in half, and then square it, and you'll know what number goes right there. And that would be +1. But since I've just added 1 to the left side, I also need to add 1 to the right side. Okay? And remember, there wasn't an invisible 0 there because I had moved everything over to the left side of the equation. And so the graphing form of my equation has my x squared by itself, my entire y grouping is now a perfect square, and it collapses down into y plus 1 squared, and it's equal to 1. And so I want to make sure you guys understand that this equation is perfectly correct. It's perfectly complete, but this is the better equation because it does confirm that my center is located at 0, -1, and it does confirm that my radius is 1, which if you go back and look at the graph, you can graphically confirm that that is what happened with your circle. So this circle has symmetry over the y-axis, and it has symmetry over the y-axis because of the fact that there's sine in the equation. Now, does anybody know why the circle happened to shift down instead of up? Well, you may have guessed, but it's because of the -2 in front of the sine. So this is what tells us that it was a vertical circle shift, and this is what tells us two things. It tells us that it went down because it was negative. If it had been positive, it would have gone up. But our circle also started at 0 and it went 2 units out. So it also tells us that our diameter is 2 units for our circle. So what we need to do is we need to come to some conclusions so that we don't have to do tables and graphs for all of these. So when we graphed r was equal to a constant, we had a circle with a center at the pole, which is 0, and then any angle, 0, 0 degrees, 0, 180 degrees, all puts you at the pole. And whatever that number was your radius. Remember that the negative number doesn't matter. It doesn't mean that your radius is negative. It just means that when you're plotting the points, you're headed the opposite direction from your angles to plot those points, but your radius still ends up being whatever that constant number is. Then the next example that we did had r was equal to a times sine of theta, and so this one was our vertical shifting. So this is going to place the center of the circle above or below the pole. And once again, whatever determines that is based on what that a value is. The one that we graphed had this type of a value. A was less than 0, so that placed our circle below the x-axis. It shifted down the y-axis. And so that means that if a was greater than 0, our circle would be above the x-axis, meaning it would have shifted up the y-axis. It's got symmetry over the y-axis because of sine being in the equation. And you only need to plot the first few points because the others are going to be symmetric. So we didn't have to do the table with all of the points plotted. And so that's one of the things you want to do. You might even want to make flashcards. Start learning to identify the equations and the shapes just by looking at them, because then you'll know how many numbers you need to do in a table of values to draw the graph. Also remember that that a value wasn't actually the radius of the circle. A is the diameter of our circle. Our circle spanned 2 units because our equation had a 2 in the front of it. And so what that means right here is that the radius is half of that number. So in our case, our radius was 1. And so what that means is that we need to come to some conclusions. We did r was equal to a constant times sine. So if we did r was equal to a constant times cosine, you need to take a second and figure out what that would mean as far as where the center would move. And hopefully you're guessing that it's going to move right or left of the pole, because cosine is typically associated with the x variable, and so that means that we're going to be doing our horizontal shift. And it also means that we're going to be symmetric across the x-axis. So if we're shifting left or right, then what that would mean is that if A is bigger than 0, then it would move in the positive direction. So it's going to move to the right of the y-axis. And if A was less than 0, the circle would be to the left. We still only need to plot 4 points, and the others are still going to be symmetric. They're just going to be symmetric over a different axis. And that A value is still telling you your diameter, so your radius is still half of that number. Okay, so I want you to practice by looking at these two equations and identifying as many things as you can about the graph just from the polar form of the equation, because that can also save you the time of converting it to its Cartesian graphing form. If you can identify the center and radius, you don't need to actually convert. You can simply write the Cartesian equation. So take a second and pause and do that. Okay, hopefully you paused. And now what you need to do is you need to see how many of these characteristics you were able to do. So this is a circle. It's been shifted to the right of the pole. It's going to be symmetric over the x-axis. It's got a diameter of 4, which means it's got a radius of 2. And so that also actually tells me where the center of it is. It tells me that it's 2 units out towards 0 degrees. Because, not that I want to sketch it all the time, but visually what this is saying is that I've got a circle that looks like this. It's got a diameter that's 4 units across, radius that's 2, so that would put the center right there. Okay, and so what that means is I can write the Cartesian equation without actually having to go to the trouble of converting it. I have a Cartesian equation that would be x minus 2 squared, because it was shifted to the right 2 units, plus y squared, because it was not shifted anywhere vertically, and its radius is 2, so it's going to be equal to 4. Or you can actually convert the polar equation into Cartesian form and then complete the square. Okay, so pause again and try the final one, and then we are done with circles. Okay, hopefully you paused again. And so now what we have here is we still have a circle, but this one has been moved below the pole, or below the x-axis. So because sine is in the equation, it's going to have symmetry over the y-axis. It's got a diameter of 3. Remember that the negative doesn't impact the actual distance of it, which means your radius is 1.5, or 3/2. And that also means that your center, and once again, if you're just mentally visualizing this, we don't want to have to draw them all the time. It looks like this. It's got a diameter of 3, so the center of it is right down there. And that is 1.5 units towards 270 degrees. Or you could have even written that it was negative 1.5 units away from 90 degrees. Either one is their equivalent for the center. And so the Cartesian form of this would have just x squared, because it was not shifted right or left at all. It would have y plus, I'm going to write it as a fraction because I like fractions, 3/2 squared. And it's equal to 9/4 because its radius is also 3/2, and then it gets squared. Okay, so that's it for circles, and then you can take a break and then you can do lines as a separate set of notes.